We're very happy to have Jesse Cohen for this week's Western Hemisphere Virtual Symplectic Seminar, speaking on composition, DG modules, and cobordism maps.
Great, thank you, Catherine. Just as a rough outline, basically the first half of the talk is going to be some background on bordered Floer homology, although I think many people here are fairly familiar with it. And I'll give an overview of the overall goal, and then the second half I'll talk about the main result of the paper. A couple of quick notes. I'm going to be working over F2 throughout the whole talk. Everything is nice and easy over F2, and so everything just works. And all of our manifolds will be oriented, so I won't say that every single time. So in classical Heegaard Floer homology, one associates to a closed three-manifold Y, closed-oriented three-manifold Y, graded F vector spaces, HF hat, HF minus, HF plus, and so on and so forth. And these are homologies of chain complexes which arise as variants of Lagrangian Floer complexes for tori in symmetric products of surfaces, which are associated to Heegaard diagrams for a three-manifold. So these are combinatorializations of the three-manifold. For us, we're going to focus on CF hat because we want to work with three-manifolds with boundary, and CF hat is the only one of these that has been sort of fully extended to three-manifolds with boundary. To a cobordism between closed-oriented three-manifolds, one gets homomorphisms, F hat of W, from one Heegaard Floer homology to another Heegaard Floer homology. And of course, these are induced by chain maps. And these chain maps count holomorphic triangles in the symmetric product. And of course, there are other ways of defining these maps. So my advisor, Robert Lipshitz, has a cylindrical reformulation, and so you count triangles and more or less what one can think of as like a thickened cylinder over the surface. But I won't go too deep into the weeds with that. Bordered Floer homology, which is due to Lipshitz, Ozsváth, and Szabo, associates to a surface plus some combinatorial data a finite dimensional differential graded algebra A of F over F2. And in its sort of simplest form, to a three-manifold with parametrized boundary parameterized by F, it gives us a finitely generated left differential module over A of minus F. And the fact that we're working with A of minus F is actually important, so I'm going to emphasize that here. And a theorem of Lipshitz, Ozsváth, and Thurston tells us that if we consider the space of morphisms of left A of minus F modules from CFD hat of Y0 to CFD hat of Y1, and we endow this with the usual morphism complex differential, then this complex is actually homotopy equivalent to the ordinary Heegaard Floer complex of minus Y0 glued along its boundary to Y1. The goal here is, if we're given three bordered three manifolds, Y1, Y2, and Y3, these are three manifolds with parameterized boundary, and if they all have boundary parameterized by the same surface, and we consider these morphism complexes, which I'm going to shorthand as more from Yi to Yj, if we consider Yij, the three manifold minus Yi glued to Yj along their common boundary, since this morphism complex is homotopy equivalent to CF hat of Yij, it's natural to ask whether or not this composition map, so the map which takes a morphism F tensor G and sends it to G composed with F, can be used to compute the map associated to some cobordism from Y12 union Y23 to Y13. because Heegaard Floer homology is sort of like a TQFT. And it turns out the answer is yes. The main theorem of my latest paper says that indeed this is the case. It says that there's a homotopy commutative square that relates this composition map to a cobordism map. And the cobordism in particular is very nice. This is the so-called pair of pants cobordism, W. The way this is defined is by taking the surface, which parametrizes the boundary of your three manifolds, and you cross it with a triangle with edges E1, E2, and E3 in cyclic order, and you glue on E1 cross Y1 along E1 cross F, you glue on E2 cross Y2 along E2 cross F, and you glue on E3 cross Y3 along E3 cross F. And the vertical maps in this homotopy commutative square are the homotopy equivalences appearing in this morphism spaces pairing theorem that tells you that the morphism spaces are actually homotopy equivalent to the ordinary Heegaard Floer complexes. So for a bit of background, the way we build these things, we need to start with something called a pointed matched circle. Everything we do here is sort of a combinatorialized version of the topology. So we start with parametrizing the boundary using some combinatorial data. And this is a quadruple. It consists of an oriented circle Z, 4K points in the circle A1 through A4K, a 2-to-1 function from this set of points to the set containing 2K elements. This is a matching, so we're pairing up the points in our circle, and some distinguished base point away from these 4K points. And this is subject to the requirement that if we surger the circle along the matching, we get a circle again. And this gives rise to a parameterized closed surface as follows. So we take our circle, which here I'm visualizing as an interval, but really these two endpoints should be matched up. We fill it with a disk, and then we attach one handles along the matching, and what results is, well, a surface with a single boundary component, which we can then fill with a disk to get a surface. And the parameterization here comes from the matching. You put a base point in that first disk and just connect arcs to the base point along the matching, and there you can see a basis for pi1 of the surface. Okay, so a bordered three manifold is actually a triple. So it's a three manifold with boundary, a pointed matched circle, and a parameterization of the boundary of this three manifold by the surface that's associated to the pointed matched circle. And such a thing can be completely specified by a bordered Heegaard diagram. So this is a compact oriented surface with of genus G with connected boundary, a collection alpha of G plus K pairwise disjoint curves in this compact surface. This consists of G minus K embedded circles and 2K arcs. So the embedded circles are in the interior, and then the arcs are transverse to the boundary and always have their ends in the boundary. And then we have G pairwise disjoint embedded circles in the interior and a base point away from the curves. And this is subject to the requirement that, well, if we delete any one of these collections of curves, the result is still connected, and any intersections between the collections of curves is transverse. So for example, I've drawn one here. The way to read this is that this vertical line, this oriented line with a base point Z, should again be thought of as a circle, and we should think of filling that in with a disk, and then these two little circles, A and upside down A, really one should think of a handle coming out of the board and at A, and then attaching to this other circle at upside down A. And then the curves that are drawn here, well, these actually tell us a recipe for building a three-manifold with parameterized boundary. I need to turn the page there. And the way this works is you take your surface, you thicken it, you glue on a copy of 0, 1 cross the surface associated to Z in a manner that's sort of perpendicular to a Collar neighborhood of the boundary of sigma. You attach three-dimensional two handles along the beta circles in sigma cross 1 and the alpha circles in sigma cross 0. And then you extend the alpha arcs in sigma cross 0 across the cores of the one handles in f of Z. And then glue on three-dimensional two handles and fill what's left with three balls. Okay. So to any sufficiently nice bordered Heegaard diagram for Y, Lipshitz, Ozsváth, and Thurston associate a left differential module over the algebra A, which is A of minus Z, determined by the pointed matched circle given by the boundary of sigma, the boundary of the alpha arcs, and then the alpha arcs thought of as the matching itself. So for this simplest example, which describes the torus, this algebra is actually a path algebra quotient. It has two idempotents, iota 0 and iota 1, and then three paths, subject to the relations that you can't go backwards along a path. So row 2 times row 1 is 0, and row 3 times row 2 is 0. And what one can think of here is that this algebra is generated by so-called Rabe chords in the pointed matched circle. So these are upward-oriented arcs between the base points in the collection A under concatenation, and we're not allowed to go backwards. You can't continue in the direction of the circle if you multiply row 2 and row 1 in the wrong order. In this particular case, the dimension of the algebra is 8, and the differential is trivial. But if you consider more complicated pointed matched circles, you do get non-trivial differentials showing up. So to actually construct CFD hat, one looks at what are called generators for our Heegaard diagrams. So if H is a Heegaard diagram, a generator is a G-element subset of intersection points between these collections of curves, satisfying two properties. Exactly one of these points lies on each beta circle and each alpha circle, and then at most one lies on each alpha arc. And if we let S of H be the set of generators, the algebra A contains a subalgebra I generated by a distinguished set of orthogonal idempotents acting on the vector space generated by S of H. And the way it does so is these idempotents correspond in a nice way to the matchings given by the pointed matched circle. And for CFD hat, the idempotent corresponding to a generator is the one that corresponds to the matchings, the arcs in the matching that X does not sit on. So the idempotent for X is going to be the one that, well, how should I say this? X is going to be killed by anything that, any idempotent that looks like an arc in the Heegaard diagram that extends out to the boundary from one of the points in X. And then to define CFD hat, you take A tensored over I with the vector space generated by these generators for H, and the differential is given by an appropriately chosen A-weighted count of moduli spaces of holomorphic disks from X to Y. So in a bordered Heegaard diagram, what one will see is disks extending from x to y with boundary on these collections of curves, but there will be some asymptotic condition where they can extend out to the boundary. So for example, if we look at this Heegaard diagram for the infinity framed solid torus that we saw before, there are three generators because this is genus 1. So we have R, S, and T. The idempotents are iota 1 for R and for T, and iota 0 for S. And the differential of, for example, 1 tensor R is rho 2 tensor S plus 1 tensor T. And one can see the disks corresponding to each of these terms in the diagram here. So there's this disk that goes from R to S and extends out to the second rib chord in the boundary. And then there's a disk in the interior that goes from R to T. And similarly, the differential of 1 tensor S is rho 1 tensor T because there's a disk that extends from S to T and goes out to the boundary at rho 1. Okay. So onto the main content. This theorem of Lipshitz, Ozsváth, and that should say Thurston. Sorry. That the morphism space from Y1 to Y2 is homotopy equivalent to CF hat of minus Y1 glued to Y2. I'm going to give you a short outline of it. Everything here is stated in terms of A infinity algebras, A infinity bimodules, and there are these funny box tensor products. If you're not comfortable with that, just substitute DG modules, DG algebras, and just ordinary tensor products or derived tensor products if you're comfortable with those. This box tensor product is a simple model for the derived tensor product. So there's something called an alpha beta bordered Heegaard diagram. This is a bordered Heegaard diagram that now has two boundary components. And that one can associate to a pointed match circle Z, with the property that, well, whatever bordered Heegaard Floer homology associates to AZ of curly Z is actually isomorphic on the nose to the algebra A as an A infinity bimodule. Bordered Floer homology associates to any one of these things several different bimodules. So there's a CFAA, there's a CFDD, there's a CFDA, and a CFAD. It doesn't really matter. Just think of generators and counting disks. And I'll actually give you an example in a second. And if one has a bordered Heegaard diagram H1 and a second H2 for Y1 and Y2, if you glue on minus H1 to AZ and minus H2 to AZ on either side, you get a closed Heegaard diagram for minus Y1 glued to Y2 along their common boundary. And by the tensor pairing theorem of Lipshitz, Ozsváth, and Thurston, CF hat of this three manifold is homotopy equivalent then to CFD hat of Y1 bar. So this is the linear dual of CFD hat of Y1, tensor CFAA of AZ, tensor CFD hat of Y2, which is then isomorphic to CFD hat of Y1 bar, tensor A, tensor CFD hat of Y2. And this is what one can show as isomorphic to morphisms from CFD hat of Y1 to CFD hat of Y2. And to see this, call a morphism basic if there are generators U and V and an algebra element rho with the property that f of U is rho V and f vanishes on other generators. Do note this does depend on our choice of bordered Heegaard diagrams, but that's okay. And one can show that the basic morphisms actually form a basis for the morphism space, hence the name. And this particular morphism, f, that's determined by f of U equals rho V, we can just identify this with U bar tensor rho, tensor v, and u bar here is the dual basis element. This diagram AZ, the simplest one for the genus one-pointed matched circle, looks like the following. And it's actually very easy to identify the generators of this diagram with algebra elements. In general, you might have many intersection points between the curves in your diagram, but what you can do if you have one of these things is draw a triangle, the largest possible triangle that sits above each of your intersection points, and follow it out to the boundary. The data of the pointed matched circle actually occurs in this picture. So here, to actually get AZ, you have to glue some little arcs together at the top of the diagram, and they're glued along the matching in the pointed matched circle. And so here, one can see that above this point that I've labeled row 1, 2, the largest possible triangle goes out to the segments that are labeled 1 and 2. And this actually identifies this particular intersection point in the diagram with the algebra element row 1 times row 2 in the algebra. So the key result for the main theorem of my paper is due to Denis-Roux. There's a bordered Heegaard triple, although he doesn't state it quite in this way, which I've called AT, with the following two properties. If you forget any one collection of curves in AT of Z and fill the now empty boundary component, you get a copy of AZ. And the map from A tensor A to A that you get by counting rigid holomorphic triangles in AT of Z actually gives you the multiplication map on the nose. And because I want to be agnostic about what I call my arcs, I'm going to call the curves in AT gamma, delta, and epsilon rather than alpha, beta, and gamma as a sort of standard. So to understand why this is important, let's actually think about what the composition map does. So this map that sends F tensor G to G composed with F can be thought of in the following way. If F and G are basic and have non-zero composition, then we can write F of U equals rho V and G of V equals sigma W for some U, V, and W and algebra elements rho and sigma. And G composed with F of U is going to be rho sigma W. And under this identification that we wrote down, that I sketched for you, you can think of the composition map as a composite. So first we send U bar tensor rho tensor V, tensored with V bar tensor sigma tensor W, to U bar tensor rho tensor V bar of V tensor sigma tensor W. But V bar of V is actually just the idempotent corresponding to V. So the evaluation map here is valued in the subalgebra of idempotents. So we get U bar tensor rho tensor iota V tensor sigma tensor W. And then one can just send this to U bar tensor rho tensor sigma tensor W via an isomorphism. And then finally, one sends this to U bar tensor rho sigma tensor V. Sorry, that should be W. Apologies. U bar tensor rho sigma tensor W by the identity tensor, the multiplication map tensor, the identity. So you should expect the composition map to be related to counting holomorphic triangles in some diagram that contains AT as a subdiagram. And indeed, this is the case. So to extend AT to give you the diagram that you need, if you start with a bordered Heegaard diagram, just an ordinary bordered Heegaard diagram with a single boundary component, sigma alpha beta 0 Z, you can get a bordered Heegaard triple H plus. And the way you do this is you take your beta circles and you just take a small Hamiltonian translate of them. So for example, if H contains a configuration like this, then H plus will contain a configuration like this at the bottom here. So we've just taken our beta 0 curve and we've wiggled it a little. This triple gives us a linear map. And I need to unpack this for you a little bit here. From CFD hat of H tensored with SFC of sigma bar beta 0 beta 1 Z. SFC here is the sutured Floer complex. What we have here, if you delete the curves that go out to the boundary, is an ordinary Heegaard diagram with a disk removed. This is the same thing as a sutured Heegaard diagram. And that disk is removed precisely at the base point. So there's actually an identification of the sutured Floer complex with an ordinary Heegaard Floer complex. And because beta 1 is obtained from beta 0 by a small Hamiltonian translate, this is going to be Heegaard Floer complex for a connect sum of S2 times S1s. And this map lands in CFD hat of H. And the way you get this map is just by counting holomorphic triangles that connect generators in H+. And a sort of standard lemma is that, well, under the identification of the Heegaard Floer homology of a connect sum of S2 times S1s with the exterior algebra on H1 of S2 times S1, or a connect sum of S2 times S1s, there's a canonical top-graded generator. So if you pick a cycle representing this generator, the map from CFD hat of the alpha beta 0 Heegaard diagram to CFD hat of the alpha beta 1 Heegaard diagram that you get by sending a generator X to the result of applying this map that we got from the Heegaard triple to X tensored with theta top. This is actually an isomorphism which is homotopic to the, quote, nearest point map. So what this nearest point map does is it sends a generator, which again is a subset of the intersection of alpha and beta 0, to its nearest neighbor point in alpha intersect beta 1. So you just sort of follow what happens to the intersection point along the isotopy, and you send each intersection point to at the start of this path to the end point of that path. Now, if we have three bordered Heegaard diagrams, H1, H2, and H3 for our three bordered three manifolds, Y1, Y2, and Y3, the diagram that we actually will care about is what I call AT123, and you get this by gluing H1 plus, H2 plus, and H3 plus to AT along the three different boundary components of AT. So there will be a boundary component that is met by the gamma arcs, a boundary component met by the delta arcs, and one met by the epsilon arcs. And we think of H1 as being gamma bordered, H2 as being delta bordered, and H3 as being epsilon bordered, and then you glue those in. And the claim is that an appropriate restriction of the triangle counting map for this new diagram is actually homotopic to F tensor G maps to G composed with F. So a very brief sketch of this is that if we think of instead just AT union H2 plus along the delta boundary, you get a differential bimodule homomorphism from A tensor CFD hat of what you should think of as being H2 tensor CFD hat of H2. This should be bar, sorry, there should be a bar above the second CFD hat, tensored with A to A, given by counting holomorphic triangles in this sort of smaller subdiagram, which have corner at the bottom graded generator of the sutured Floer complex of beta 2, 0 and beta 2, 1. So this here, this sutured Floer complex is for the sutured Heegaard diagram that you get by forgetting the collection of curves meeting the boundary in H2 plus. This map is homotopic to the map that sends rho tensor U0 tensor V1 bar tensor sigma to rho times V1 bar of U1 times sigma. Here U1 is the nearest point to U0. And the proof uses a non-existence lemma for holomorphic triangles in AT, which meets the boundary of AT, alongside of, yeah?
Can you say again what the AT stands for?
Sorry, AT stands for a root triple. It's a triple diagram that that gives you 3 copies of this AZ diagram that I gave you a picture of here. So the way to think of how to get this is you just drop vertical lines from these intersection points at the top boundary all the way down to the bottom boundary of the square. And then you perturb it a little bit so that you can get rid of the non-generic triple intersection points.
I see. Okay.
And you also have to identify a couple. You have to identify 2 arcs in one of these boundary, one part of the boundary here. So you have to identify an arc here and an arc here. Yeah. Great. Okay, so it turns out that as long as you choose your perturbations very carefully, there are no holomorphic triangles in AT which meet the boundary. And this is actually very, very delicate. You have to sort of choose everything very precisely. This also uses a pairing theorem for triangles due to Lipshitz, Ozsváth, and Thurston. And the fact that H2 plus is obtained by a small perturbation then allows us, together with all of this, up to homotopy, to only count product type moduli spaces. So these moduli spaces depend on some homology classes. And at the end of the day, you end up counting moduli spaces of triangles that connect 3 algebra generators and these U0 V1 bar and the bottom graded generator. So you really, at the end of the day, only need to think about sort of triangles in the interiors of the 2 diagrams that you glued together. And a corollary of this is that if you work a little bit harder, there's this composite map from this tensor product of morphism spaces to the third morphism space, given essentially by precomposing the cobordism map, or the triangle counting map that you get by looking at this diagram AT123 with a 1-handle cobordism map and post-composing with a 3-handle cobordism map. And this turns out to be homotopic to the composition morphism. Okay, so there's going to be a bit of a jarring transition here. What we need now is to actually understand why G hat of AT, or G hat AT, is actually a cobordism map. So what I'll do is I'll sketch for you a geometric construction and then appeal to work of Ian Zemke, which will tell us that indeed the map that we started with corresponds to a cobordism map, and it corresponds to the correct one. So just as a bordered Heegaard diagram specifies a bordered 3-manifold, a bordered Heegaard triple actually specifies a cobordism of such objects. And this takes the form of a cornered 4-manifold with connected boundary stratum that consists of 3 bordered 3-manifolds, y, eta, theta, for each pair of collections of curves, gamma, delta, or epsilon. So, eta not equal to theta in gamma, delta, and epsilon. And for each collection of curves, eta, that meets the boundary of this triple, there's a facet, or what I call a facet, which you can think of as a regular neighborhood of the result of gluing an additional disk to the surface of the surface associated to the eta pointed matched circle. So, so in this construction of the surface at the very beginning, we filled our pointed matched circle with a disk, and then attached some one handles. All you need to do here is attach another disk along the pointed matched circle after constructing the surface. And this gives you a cobordism from 2 copies of the surface to S2, and this ultimately is going to be a regular neighborhood of this sort of singular surface. And these 2 pieces intersect in the corner stratum, and there are no higher codimension strata of WH. The crucial proposition is that if you have 2 bordered Heegaard triples that share a common boundary matching, then the 4 manifold that you get by from gluing the 2 Heegaard triples and then applying this construction is the same as, well, first constructing each of the cobordisms individually and then gluing them along a facet. And in particular, what this tells you is that the 4 manifold associated to this closed Heegaard triple AT123 is obtained by gluing each of the individual cornered 4 manifolds to the cornered 4 manifold associated to AT. And then with a little more work, you can show that the pair of pants cobordism that we started with is obtained from W of AT123 by first pre-composing with a 1-handle cobordism and post-composing with a 3-handle cobordism. So what happens in the middle here, the reason you don't get the pair of pants cobordism on the nose is you had all of these beta circles that were perturbed slightly. And so at the ends of WAT123, you have a whole bunch of connect sums of S2 times S1s that show up. And you need these 1 handles and 3 handles to cancel them. But this is actually good because we claimed that G hat AT is homotopic to the composition map. And G hat AT was, well, the map associated to AT123 pre-composed with a 1-handle map and post-composed with a 3-handle map. And it's exactly the 1-handle map and 3-handle map corresponding to the 3 handles here and the 1 handles here. Okay, and the corollary of this is, well, the map associated to the pair of pants cobordism is homotopic to the composition map. So this uses the fact that G hat of AT is composite as homotopic to the composition map, this fact about the pair of pants cobordism, and then a few theorems of Ian Zemke that identify triangle counting maps for an arbitrary triple with the map induced by the cobordism represented by that triple. And the subtlety here is that in Ozsváth and Szabó's original construction, you need Heegaard triples that are subordinate to a bouquet that describes the cobordism as surgery on some link. So a priori, it's not obvious that the triangle counting maps for an arbitrary triple actually give you the correct cobordism map, but they do. And I believe that is what I had. So finishing a little early here.
Thank you. Thanks very much.
Thank you very much. Thank you for inviting me.
Are there any questions for Jesse?
Can I ask a question?
By all means.
So your main theorem about identifying these 2 different operations, are there any particular geometric applications that you have in mind for that?
There is an application that I have in mind, which will actually appear in an updated version of the paper very soon. I'm just working on writing everything down. The main application here is actually that this gives you an algorithm for computing cobordism maps on HF hat in general. So if you start, for example, if you have a cobordism that's built entirely out of two handles, and you start with a bouquet that describes this cobordism, if you what you can do is take a regular neighborhood of the bouquet and its complement. Those are two handle bodies, and then you can look at what you get after doing surgery. That gives you a third handle body, and this the composition map here, well, if that corresponds to the pair of pants cobordism, well, that pair of pants cobordism is exactly the cobordism considered by Ozsváth and Szabo. And so this composition map actually does genuinely compute for you the cobordism map associated to that triple. And the nice thing about this is that, well, there's an algorithm for computing CFD hat of handle bodies given by Lipshitz, Ozsváth, and Thurston in their paper, Computing HF Hat by Factoring Mapping Classes. So this can all be implemented on a computer, and morphism spaces are relatively easy to compute once you know the DG module associated to the handle body or bordered through manifold. So like in practice, these morphism spaces might be somewhat large. I've done, I don't know, a few hundred computations by hand. And, you know, they might have 30, 40, 300 generators or something. But just computing the differential is really, really easy once you know what all of the input data is. And it's then very easy to compute what composition does.
Mm-hmm. Okay, got it. Thank you.
You're welcome.
I have a basic question, which is,
Sure.
Can you say again what this box product is that you
Oh
had
boy.
earlier?
Sure. So the box product, the box product is a sort of finite dimensional model for the derived tensor product. So really secretly what's going on here, let me find it. Secretly what's going on here, say in this line, CFD hat of Y1 bar is really a right A infinity module. What's happening with this box tensor, oh no, sorry, this is a right type D structure. A is a left A infinity module, and a right type D structure you can think of as being a right differential module, but instead of encoding a differential as a sum of algebra elements times basis elements, what you do is you just keep track of this information by sending a basis element u, say, to the sum of algebra elements tensored the corresponding basis elements in the differential. And so instead of having to think about a whole, big module, you really just need to think about a basis. And so you can think of this as a map from CFD hat to CFD hat tensored with A. And so you're sort of splitting algebra elements off of your basis elements. And then you can feed that in to the A infinity operation in of A here. A is really an A infinity bimodule. Although for, as written down, it's really a DG bimodule. But so you take your algebra element, you feed it into multiplication. And so that, the operation that underlies this box tensor product is just the ordinary tensor product, but it changes the differential in a sort of complicated way. And in general, when you really do have proper A infinity modules and type D structures, this will be a potentially very large but finite sum of things, like to actually compute the box tensor product. You have to think about splitting off multiple algebra elements and feeding multiple algebra elements into the infinity operations.
Very cool.
Yeah.
Well, are there other questions for Jesse? Okay, well, thanks very much for the talk. Really appreciate it.
Much.